Okay, we're going to be looking at question 3, difference equations. Consider the system of differential equations. X t plus 1 minus xt is equal to minus a xt plus b yt plus x0, and yt plus 1 minus yt is equal to minus a yt plus b xt plus y0. Write the system as a vector of xt plus 1 minus a vector xt is equal to some matrix M multiplied by vector xt plus vector x0, and determine the matrix M and the vector x0. Cool. So this is pretty straightforward. The vector xt plus 1 is just xt plus 1 and then y t plus 1. So all I've done is basically just stack these two differential equations on top of each other, with this one in the first row and this one in the second row. And then that follows on when we have the vector xt is equal to, so now we have minus a xt plus b yt, and then minus a yt plus bxt. So that's just me stacking this on top of this, and then we're going to plus this with x0 and y0. So this, hopefully you can notice, is just the vector x0. So the vector x0 is just x0, y0. Now this we can write as, like they've said, some matrix and then the vector xt and yt. To figure out what this matrix is, we're just going to look at the coefficients of xt and yt. So the coefficients of xt is minus a, the coefficients of yt is b. So when we multiply this row by this column, we are going to get minus a xt plus b yt. And if we look at these two, the coefficient of xt is b and the coefficient of yt is minus a. So when we multiply this with this column, we are going to get minus a yt plus bxt. So our matrix ends up being minus a, b, b minus a. Cool. Hopefully that made sense. Calculate the stationary state. So the stationary state just means that there is no longer a difference between these two times. There's no difference between this time and the time of the next year or the next period, whatever it is in this question. So essentially, xt plus 1 is going to be equal to xt, which means that xt plus 1 minus xt will be 0. So we're going to equate this to 0, and that just means we have 0 is equal to the matrix M multiplied by the vector xt plus x, the vector x0. Now, in order to solve for xt, which in this case is going to represent our steady state, we are first going to move this to the other side. So we have minus x0 is equal to m multiplied by, I'm going to change this so that it's now xs, which just stands for steady state. And in order to get rid of this matrix, we have to times by the inverse of that matrix. So the steady state is equal to minus the inverse of m multiplied by the vector x0. Now, the inverse of m is going to be 1 over the determinant, which is a squared minus b squared, brackets minus a minus a minus b minus b. Hopefully we know how to work out the inverse of a 2 by 2 matrix. And so what that gives us is the steady state is equal to 1 over a squared minus b squared. If I take this minus sign into the matrix, we get a, b, b, a, and then we're going to multiply this by this vector, which is x0, y0. And so we get 1 over a squared minus b squared, that should say, brackets ax0 plus by0, and then bx0 plus ay0. So our steady state is ax0 plus by0 all over a squared minus b squared, comma, bx0 plus ay0 all over a squared minus b squared. Cool. So if we just rewrite that into here, this is what we get. Moving on. Number C, determine the conditions on A and B, which are greater than 0, for which the stationary state is stable. Sketch this area in the A, B diagram below and give the general solution in vector form in terms of the vector x0, the stationary state vector, and a time-dependent matrix B. Okay, cool. If I rewrite our difference equation, this is what we have so far. I'm now going to move this to this side, to the other side, so that we get 1 plus m, and then the vector xt plus x0. Hopefully that made sense. And now, to test for stability, this is a discrete time system. So this is a discrete time system, and because of that, the stationary state is stable if and only if all the eigenvalues of A satisfy that the absolute value of the eigenvalue is less than 1. So if we work out the eigenvalues of this matrix, which is having an effect on how this difference equation changes, we will first have to work out the characteristic equation. We do that by doing the det of this matrix 1 plus m and minusing it by lambda I and equating that to 0. So if we write down this matrix, it is 1 minus a minus lambda, b, and then 1 minus a minus lambda. And we need to work out the determinant and make it equal to 0. So we do these two multiplied by each other, and then minus b squared is equal to 0. When we expand these two brackets, we get 1 minus a minus lambda minus a plus a squared plus a lambda. And collecting up the like terms gives us... Cool. So if we now use quadratic formula to work out the eigenvalues, we get minus 2a plus 2, so that's minus b, plus or minus square root b squared, which is going to be 4a squared minus 8a plus 4 minus 4 times c, where c is all of this. So minus 4a squared plus 4b squared minus 8a minus 4. So this and this cancel out, this and this cancel out, and this cancel out. And all of this is over 2a, so just over 2. So we get minus a plus 1 plus or minus square root of 4b squared is 2b. 2b divided by 2 is just b. It's plus or minus b. So our first eigenvalue is going to be minus a plus b plus 1. And our second eigenvalue will be minus a minus b plus 1. So now, if we go back to the condition that these eigenvalues need to satisfy, it is that the absolute value of the eigenvalue has to be less than 1, or we can write this as has to be between 1 and minus 1. Cool. If we now use this condition on this first eigenvalue, we have minus a plus b plus 1, and that has to be less than 1. And we also have minus a plus b plus 1, which has to be greater than minus 1. So that gives us minus a is less than minus b, or a is greater than b. And over here, it gives us a minus b is less than 2. Hopefully you can see that. If we do the same thing for the second eigenvalue, we have minus a minus b plus 1 less than 1, and minus a minus b plus 1 is greater than minus 1. When we work this out, we get minus a minus b is less than 0, so a plus b is greater than 0. And over here, we have minus a minus b is greater than minus 2, or a plus b is less than 2. So hopefully we can see that a plus b greater than 0 is not needed, because in the question it says that a and b are both greater than 0. So adding two numbers that are greater than 0 is obviously going to be greater than 0. So this condition, not really needed. It's already said over here pretty much. So that means this condition is needed. If we then look at this inequality, it says a plus b is less than 2. So we have a plus b is less than 2, and we also have a is greater than 0 and b is greater than 0. So as we have these conditions, it just means we don't need to write this condition, because this condition can be inferred from these conditions. So this condition is not needed, and therefore this one will be needed. So the conditions on A and B is that A has to be greater than B, which has to be greater than 0, and then A plus B has to be less than 2. So these are the two necessary conditions for A and B. If we now look at this graph, rewriting our conditions A, B are greater than 0, and A is bigger than B, and A plus B is less than 2. What this means is that when I split this up into 4 quadrants, we only want this first quadrant because that is where A and B are both going to be greater than 0. If I now look at this inequality, we have A plus B is less than 2. So that means if I pick these 2 points, 0, 2, and 2, 0, it would satisfy this equation. But of course, we don't want to satisfy this equation. We want everything less than this equation. So it's going to be a dashed line, and we want everything that is underneath here. So that's us drawing this inequality. Now, if we look further at A is greater than B, if we draw A is equal to B, we will just have a straight line, which is the same as y is equal to x. So it looks something like this. Of course, it's going to be a dashed line because we don't want to fulfill this. We want to fulfill A is greater than B, not A is greater than or equal to B. All the points where A is going to be greater than B is going to be underneath this line. So the region that satisfies both of these inequalities would be this triangle over here, where this point is 0, 0, this point is 2, 0, and this point would be 1, 0. Hopefully that made sense. So conditions on A and B is that A is greater than B, and they're both greater than 0, and A plus B is less than 2. Cool. Next step is to find a general solution of the vector xt. In order to do this, I'm first going to define another equation which is just going to show small deviations away from the stationary state. So xt is equal to a small deviation plus that stationary state. I'm now going to substitute this back into our previous equation. which is this one over here. When we do that, we get delta t plus 1 plus the stationary state vector is equal to 1 plus m delta t plus 1 plus m stationary state plus x0. Expanding everything out, we get this. So we can cancel out these two. They're both equal. They're going to cancel out. And if we look at this, previously, to work out the stationary state, we had this equation, which we can write m multiplied by the vector xs plus x0, the vector x0, which is going to be equal to 0. If we look at this equation and look at this, they're both the same thing, and we saw that these are added together is going to equal 0. So these two cancel out. And so we're left behind with delta t plus 1 is equal to 1 plus m delta t. If I let t is equal to 0, just to see what happens to these deviations when t is equal to 0, we get delta 1 is equal to 1 plus m 0. And if I let t is equal to 1, we get delta 2 is equal to 1 plus m delta 1. And we can substitute this back in. So we get this, and finally we get 1 plus m to the power of 2 delta 0. And when we sub in 2, it would be to the power of 3 and so on. So whatever this number is, it is 1 plus m to that power. So what that means is when we have t over here, we will have 1 plus m to the power of t delta 0. Hopefully that made a bit of sense. If I now substitute this equation back into this equation, which shows how we deviate away from the steady state, we get xt is equal to 1 plus m to the power of t delta 0 plus x steady state. If I now change this again by using this same equation, but I'm going to sub in t is equal to 0, I get the vector x0 minus the steady state vector plus xs. And now, if we go back to the question wanted us to find a time-dependent matrix bt, and as we can see, this is our time-dependent matrix, 1 plus m to the power of t. As we can write this as 1 minus a, b, b, 1 minus a, to the power of t. So this is what bt is equal to. So if we write this down, we have bt dot x0 minus the vector of the steady state, and then plus the steady state. And this matrix is 1 minus a, b, b, 1 minus a, all to the power of t. Hopefully that made sense.